I guess that's interesting. Yeah. Makes sense.
Right. So yeah, sorry. I think probably the further discussion can be moved to the Slack, and our co-host will put the Slack link there, if that's fine. Yeah. So yes, then thank you, Holin, again for the very nice talk. And then the time will be given to the next speaker, Ming-Lei. So you can open your mic and share your screen and get started.
Okay. Okay. Hi everyone. This is Ming-Lei Xiao. So can you see the screen?
Yeah. Could you make it full screen?
Sure. Is it good now?
Yes, please.
Okay. It's my honor to have the opportunity to introduce my recent work on effective field theory, and many thanks to the organizers of the conference. My topic is a preferred basis for effective field theories. In the previous talks, Professor Yu and Dr. Li have introduced our way of deriving a complete operator basis with systematic treatment. Here, I'm going to move on to another aspect of the operator basis that focuses on the quantum number, especially the angular momentum. When it comes to angular momentum, it is natural to think about partial waves. We'll start with a brief review of partial waves in scattering theory and inspire the generalization of them. Together with the gauge structures, we construct the so-called J bases, which not only have definite angular momentum, but is also in the irreducible representations of the gauge groups. It also induces an operator J basis. In a few examples, we're going to show that in certain applications, such as loop integrals or the analysis of UV origins of the operators, this basis stands on a unique position among the other bases. Okay. In a scattering problem, we decompose the multi-particle wave functions into partial waves with definite angular momentum. The multi-particle state, usually described by a tensor product of single particle states, is actually in the tensor representation of the Poincaré group with momenta, spins, and spin components of each particle. The partial wave state with definite total angular momentum is in the irreducible representation of the Poincaré group. So therefore, this decomposition is similar to the composite of spins. The difference is being that the group is Poincaré instead of SO3, so that the momenta and especially the angular dependence are involved, which makes it a partial wave function. Therefore, the partial wave basis is formally just the CG coefficients of the Poincaré group. Due to the angular momentum conservation, the S matrix has to be block diagonal under this basis, and the diagonal elements called the partial wave coefficients carry information of the dynamics, for which we can explicitly impose the unitarity bound or convert the phase space integration into a summation. However, the partial wave basis was only well known for two particle states. In the Helicity basis, where we take the spin components along the momentum direction, it is given by the Wigner D matrix. This can be used to expand the S matrix and get a partial wave coefficient like this. We're inspired to ask the following questions. The traditional partial waves are all defined in the center of mass frame, so which is not convenient in other frames. Could there be any Lorentz invariant form? And second, is it possible to extend to more particles? And finally, as we have the amplitude operator correspondence, does the generalized partial waves, which are also amplitudes, induce any non-trivial results for the effective operators in the field theory? As to Lorentz invariant amplitudes, the first thing coming to mind is the holistic spinor formalism. We introduced the spinor variables together with a convenient massive version introduced in this paper, so that massive particles could be analyzed on the same footing. Any amplitudes are now a function of such spinors with no explicit dependence on energies or angles. We can easily find the connection between the traditional partial wave functions as D matrices and the Helicity amplitudes written in terms of the spinors. There might be several amplitudes with different external states that share the same partial wave distribution as in the first example. because the additional factor, the 1, 2 bracket here, has no angular dependence at the center of mass frame. However, they make a difference in other frames, which is easily accounted for by plugging in the values of the spinors in the new frame. Hence, the amplitude form of the partial waves have more information than the D matrices. We also see that for the same external states, there can be different amplitudes that exhibit different partial wave distributions, which means different total angular momentum for the process. From the previous talk on the Y basis, we know how to construct a complete basis of such amplitude with a given external state. But the question is, how do we pick out the correct combinations of them that have definite angular momenta? First, let me describe an intuitive construction of the partial wave basis. We introduce the auxiliary spinors from the total momentum P and consider the amplitude between the multi-particle state psi and a heavy particle with momentum P and J, spin J. The amplitude can be written as such a function of the spinor variables. All of the spinors should form brackets due to Lorentz invariance, and the little group representation of each particle should be respected. The spin J of the heavy particle is reflected by the fact that the amplitude has 2J number of totally symmetric little group indices from the spinor chi. The 2J plus 1 independent entries of the tensor represent the values of M. For two particles, such a function is uniquely determined, as shown in this paper. The powers are fixed by little group. In this paper, it was given as the unique form of 3-point amplitudes, but here I'm treating it as the unique form of two particle partial wave functions. If we put together the wave functions of initial and final states, where the dot indicates a totally symmetric contraction of the little group indices equivalent to a sum over M, the Wigner D matrices are reproduced, as verified in our paper. Note that in this construction, the auxiliary spinors chi are eliminated using the identity relation, where the little group contractions become the spinor contractions among the external spinors by the epsilon tensors. It thus implies a feature of the resultant amplitude. There will be 2J number of totally symmetrized spinor contractions between the spinors in the initial and final states that we call bridges. With this feature, we can easily find the partial wave basis in the 4 fermion example. As the scattering from particle 1, 2 to 3, 4, this is obviously no bridge in the first example. Thus, J equals 0 for this amplitude. And for the second one, there are 2 bridges. Both brackets are contracting the initial and final particles. And the contractions are indeed symmetrized. So J equals 1 in this case. Okay, it is also important that the bridges consist of the same type brackets. So in this 4 scalar case, we find that J equals 1 basis seems to have anti-symmetric contractions due to this minus sign, but both types of brackets are involved. We can convert it to a form with symmetrized same type brackets at a price of having a spurious pole. So therefore, this intuitive construction, though very useful in many practically simple cases, is not systematic enough and not available in general. Here's another approach. Just like how we find the spherical harmonics out of arbitrary angular distributions, we solve the eigenvalue equation for the operator elsewhere in the angle representation. As explained at the beginning, the partial waves are eigenfunctions of the Poincaré group. In particular, we need to study the spectrum of the Casimir operator W square with this eigenvalue, where W is the Pauli-Lubansky operator. So how does it act on the spinor functions? We know the representations of the momentum operator from the definition, which is simply a multiplicative factor. And that of the Lorentz generator is also given in literature long before, where the partial means derivatives with respect to the spinor variables. Here we introduce the sum over particles to define the operator acting on the whole multiparticle state, which as far as I know did not appear in the literature. It becomes quite non-trivial to combine the two and derive the doublet square operator, as it involves a lot of interparticle operations, which in fact take into account the contribution from orbital motions among particles to the total angular momentum. In our case, such feature makes it recognize the bridge structures in the amplitude. We can now impose this operator on a complete Y basis of a class and obtain the representation matrix W, which diagonalizes to the eigenvalues. A complete partial wave basis is then obtained as a linear combination of the Y basis. Let's apply it to the previous examples. We obtained the representation matrix for this Y basis. The eigenstates are found as the combination of the Y basis. The previous form can be reproduced by applying the Schroeder identity. Similar for the dimension 6-4 scalar case. Here we examine the particle 1,3 to 2,4 scattering. So it should be specified in this operator. We obtain the partial wave basis by diagonalizing this matrix. And it is also equivalent to the previous result, this minus sign result. So although the doublet square operator seems more involved than the bridge construction, it is more systematic and easy to implement by code. Now that we have a complete basis of Lorentz structure with definite angular momenta, an amplitude also has its gauge structure described by invariant tensors, as mentioned in previous talk. We can also find a preferred basis for the gauge structure with a particular irreducible representation for a given scattering channel. In this example, where we look at the Higgs scattering at dimension 6 level, a 2 Higgs state can be an SU2 singlet or triplet, corresponding to the 2 SU2 tensor structures. The Lorentz basis is given in the previous slide. So together, we may construct 4 amplitudes with various quantum numbers, J for angular momentum and R for the SU2 representation. We define it as the J basis with 4 coefficients. Since it is just an alternative basis for the same process, this should be the same as the other basis, like P basis defined in Dr. Lee's talk, which takes into account the identical particle issue. Schematically, we can expand the P basis onto the J basis by such a transform matrix K, so that we find the relation between the J basis coefficients and the P basis coefficients, or the Wilson coefficients. This relation shows that the 4 J basis coefficients are not independent because the J basis is an alternative basis at the flavor blind level, where the repeated fields are considered distinguishable. But still, we'll show that they're pretty useful by concrete examples. Before that, let's look at how to obtain this matrix KPJ. This is the definition. As shown in the previous talks, we can expand any operators onto the Y basis with systematic algorithm. We can do it for both the P basis and J basis, and finally obtain this formula. The KPY was obtained in Dr. Lee's talk, and the KJY on the right side consists of Lorentz part and gauge part. But the Lorentz part is nothing but the matrix diagonalizing the W squared operator that I mentioned previously. We also have a systematic treatment for the gauge part in our code, which I'm not going to elaborate here. But in simple cases lower than dimension 8, it can be done by hand with little effort. Here we show the result obtained by our code. This is the KJY, where it prints the quantum number of 2 particle states 1, 3. The first entry being the angular momentum, the second being the color representation. They are all singlet. And the third is the SU2 representation. So it reproduced the 4 J basis operator in the previous slide. And these operators are given by coordinates under the y basis. So collecting these coordinates, we get a 4x4 matrix KJY. I also show the p basis obtained by our code. You can find two combinations of two operators that have symmetric flavors for the Higgs that survive in the standard model. The two operators in Warsaw basis, for example, would be just linear combinations of these two. We also get the other two that have anti-symmetric flavors for the Higgses, which is ruled out in the standard model. But they may be useful when we consider beyond standard model extensions. Now, with these results, we can easily construct a KPJ matrix with this formula. So how is this information used in real physics study? Let's move on to the applications. The way we construct the amplitude J basis actually implies that the corresponding effective operator, also labeled by the quantum numbers, only generate a particular multi-particle state. If the operator and state have mismatched quantum numbers, it would annihilate the state. It's a little like the operator-state correspondence in the CFT. However, since we don't usually work in partial wave basis, and as long as the wave contraction exists, there's at least a non-zero component of the tensor state that match with the operator. So this rule seems trivial. But we can make use of the conservation law. Consider this scattering process where we have a mismatched state on the other side of the amplitude. Although they they don't contract directly, the diagram should vanish by conservation law. Here, M is an amplitude of arbitrary loop order. And the statement is so strong that even the problematic rational term for the loop diagram should vanish for this particular topology, of course. But how should we prepare a state with certain quantum number even on the other side of the amplitude? Well, we don't, but we can find cases where this quantum number are constrained. In our paper, we list two such cases, both for two particles. The first one is that the total angular momentum should be lower bounded by the helicity difference of the two particles. It can be easily argued by noting that the angular momentum should be no less than its component along the relative momentum. With this criterion, we can look at the contribution from the H4 d squared type operator to this amplitude at loop order, as shown in the previous diagram. The two leptons are opposite helicities, and hence the angular momentum is no less than 1. Therefore, we can only search for the contribution from J equals 1 and SU2 singlet, since the right-handed lepton is singlet, which was given by the KPJ matrix as a particular combination of the Wilson coefficients. So without any loop computation, we get a particular behavior of the loop integral. The second rule has to do with identical particles. The permutation symmetry of them in the amplitude is constrained by their total angular momentum. Consider this example with fermion loop in the middle. The operator has J equals 1 in a particular channel, which means antisymmetry of the two gauge bosons on the other side. Therefore, it does not contribute to the amplitude producing two photons or gluons because they cannot be antisymmetric, but it can produce W bosons due to this available antisymmetric tensor. Finally, let's look at how this J basis organizes the tree-level UV origin studies. For model builders, it's interesting to fit the operators into some UV ansatz with some particular heavy particles. The fact is that such diagram would directly produce the J basis operator with quantum number given by the resonance after integrating out. Now we need the inverse of the KPJ to expand the J basis onto the full P basis, where all the permutation symmetries are retained, and then examine which terms survive the number of flavors at the end. For example, this dimension 9 type operator in the standard model EFT has two P basis operators with totally symmetric flavors for both up and down quarks, out of 25 in total. so that they could contribute to the first generation process as the AN bar oscillation. If we look at this particular topology of tree diagram in which the internal lines are some heavy particles, we can find a complete set of 25 J basis operators, which decompose into the P basis like in this formula, using this formula. And the result is in this table, where we organize the 25 J bases into the 5 by 5 matrix, the rows indicating different assignments of SU3 representations of the resonances, and the columns indicating their spins. The zeros actually correspond to cases when the selection rule B takes effect. These resonance patterns are ruled out. The other patterns are found to generate 4 combinations of the 2 operators indicated by the 4 subspaces in the 2-dimensional landscape. So the experiment may give strong implications on the UV resonance pattern. In general, one could put the J basis result from multiple tree topologies together. As mentioned in Professor Yu's talk, one could find the J basis of the dimension 5 Weinberg operator in 2 different channels. The 4 UV origins, you get 4 UV origins, 3 of which correspond to the type 1, 2, and 3 Seesaw models. And the last one is ruled out by repeated Higgs fields, because there's only one flavor, so this P-base operator is ruled out. Okay, to summarize, we generalize the notion of partial waves to describe a state with arbitrary number of particles. It can be applied to decompose either multi-particle wave functions or scattering amplitudes. And based on the partial wave amplitude basis, we construct a so-called J basis of effective field theories as an alternative flavor blind operator basis. Relevant calculations are realized by mathematical code. Such a basis is special in various applications, such as in certain loop integrals. The selection rules tell us which contributions should vanish. Furthermore, we could analyze the phase-space integration as the unitarity cut of the integral, which can be written as sum over partial wave contributions. That should be elaborated by Professor Pomerol in the afternoon. We also see the landscape analysis, where J-basis information implies the UV resonance pattern. We only associated the J-basis to subspaces of the landscape, but further constraints such as positivity bound and perturbative unitarity bound could be imposed, which might reduce the landscape to even smaller regions. Okay, that's all for my talk. Thank you for your attention.
Okay, thank you. Yeah, let's see if we have any. So we can have 2 quick questions. Maybe we see if we have anyone from the room. If not, then Tom, please.
Hi, thanks for the nice talk. So I had a question on your selection rules, part 1. I think you were talking about. You made a statement about the matrix on all loop order. You mean do you mean you're allowed to also include the higher dimensional operators in the loops, or are you're sticking at the linear order in your higher dimensional operators?
Sorry, you mean this diagram?
Yeah. So M, you say it's valid to all orders of M, but you restrict to no other high dimensional operators in there?
No, the high dimensional operator is inserted here. So I don't care what the diagram there is here, because everything is already fixed by conservation law. And so as long as you look at only one diagram.
High dimensional operators can appear.
Yeah, there can be a high dimensional operator in this M.
Okay.
So yeah. Okay, so everything is fixed by like the constraints on these external legs and the quantum number of this operator. So you can put anything in this M.
Thanks.
Okay. Yeah. Thanks for the question.
Okay. So if no more questions to Ming-Lei, then thank you again for the talk, and then we can move to the next one to Tom Amelia.